Many subjects have an air of mystery to them that is revealed once they are properly learned. Quantum mechanics is an exception. Whatever confusion it instills actually only seems to increase with increasing knowledge of the subject. The lengths that physicists have gone to explain both the observations and the mathematics are extreme, yet every step forward seems to only make the subject even more incomprehensible. In a way, this is what makes the subject so compelling. For people who enjoy challenge, there really isn't anything like it. The path to discovering my theory was not a straight line, and my ideas have been refined over time. I started with a basic hypothesis. Subatomic particles have wave-like behavior, and waves quantize when they are within a boundary. So I began to search for that boundary. The Einstein field equation of general relativity is currently our best mathematical description of the geometry of spacetime. This description includes gravity, but it is perhaps more accurate to say that it is a description of how causes relate to effect. To say that nothing can travel faster than light is a bit like saying that a triangle has three sides. It's simply an aspect of the shape of spacetime. When the study of subatomic particles began to reveal their strange, inexplicable behavior, Einstein became very concerned. The mathematics that describes that behavior implies what is known as non-locality. It implies that their behavior breaks the geometric constraints which Einstein established that describe how causes relate to effect. This troubled him greatly, because if you introduce actions or even just information that can travel faster than light, relativity says that effects can happen before causes. The effect happens first, and the cause after, which is completely illogical. His famous quote, "God does not play dice with the universe," in my view, has been misinterpreted. It's presented as if Einstein simply took issue with the probabilistic aspects of quantum mechanics. But to Einstein, if effects can be non-local, then it's all cats and dogs living together, and God is a gambler. John Stuart Bell created a test, Bell's theorem, to test the non-locality observed at the Planck scale. He created these tests in the hopes that they would dispel the idea, but they did not. As non-locality is thought of today, Bell experiments have reinforced the view that the behavior at that scale cannot be explained without the causality-breaking concept of non-locality. I interpreted this incompatibility as the boundary I was searching for. Einstein's spacetime represented a fundamentally local system, and quantum mechanics represented a point of interaction between that local system and a non-local system that drove spacetime to the limit of what it could tolerate. I began to refer to Planck's constant as the non-local tolerance of spacetime, and eventually started to think of locality itself as how much non-locality is allowed. I called this the interactive interpretation of quantum mechanics, and it spawned a number of ideas, almost all of which were wrong, but one idea held up under scrutiny and eventually led to where I am now. Within Einstein's relativity, all objects can be mathematically described as moving in 4 dimensions at the speed of light. Since I considered Planck's constant and the speed of light to be part of what defines the non-local tolerance of spacetime, it made sense that when moving in 4 dimensions, the time component of that vector must be contracting with increasing velocity. This leads to a proper time-centric interpretation of relativity, which is the inverse of how it is usually interpreted. One of the issues it creates is that the proper time of light is 0, which is a very confusing idea, so I did not take my interpretation too seriously. That is, until I realized that the evidence that this is the correct way to interpret relativity already exists. The Dirac equation has fascinated me since I learned of it. The story behind it is one of a lone genius confronting his peers with what may have seemed like a fanciful conclusion, but ultimately winning the day. The Schrödinger equation revolutionized the way that physicists view quantum mechanics, but it was still based in Newtonian concepts of absolute space and time. A relativistic version was needed, and the result was the Klein-Gordon equation. This equation was widely accepted by physicists, but it produced some unsatisfying results, and Dirac felt like he understood what was wrong with it. Einstein's relativity is sometimes said to put space and time on equal footing. The Klein-Gordon equation was first order in time, but second order in space, breaking this unwritten rule. You can think of a differential equation as a circle on a Venn diagram. The answer you're looking for may be inside that circle, but to make use of it, you need more circles. You can take the Schrödinger equation, the equation that shows the Coulomb potential, Laguerre and spherical harmonic equations, and together they produce equations that show electron orbital shapes. Dirac set about fixing the Klein-Gordon equation by making it first order in space to match its first order in time, but by doing so, the equation became over-constrained. This is like saying that the circle it represents is too small, as these two symbols were believed to represent constants. Eventually, Dirac interpreted them to be matrices. This expanded the circle, but now the equation gave 4 answers for every question. 4 answers from the 2 overlapping parameters of spin and energy. It predicts that certain particles will be spin up, positive energy, spin down, positive energy, spin up, negative energy, and spin down, negative energy. Negative energy was a new idea, and Dirac argued, with conviction, that it was real, and that an entirely new class of matter existed, antimatter, and the positron, the antiparticle to the electron, was discovered soon after. This result is now legendary. Dirac, by following his instincts and mathematical rigor, and in direct opposition to the opinions of his peers, had altered physics at a fundamental level, but the way to interpret the negative energy solutions has been a subject of discussion ever since. My theory is based on a humble proposition. The Dirac equation is correct, and it does not need interpreting. The Planck relation tells us that energy equals Planck's constant times frequency, and frequency is equal to 1 over time. So negative energy requires negative frequency, and negative frequency requires negative time. This is not a new idea. It's called the Feynman-Stikelberg interpretation. But to use the word interpretation here is a mistake. Nothing has been interpreted. This is literally what the math tells us. What needs interpreting here is not the Dirac equation. It is relativity. Our inability to understand Dirac's solution and quantum mechanics in general lies in our pre-existing view of time and how we believe it functions. There are 2 mathematically equivalent ways to interpret relativity. The orthodox view, which uses the Minkowski metric, and where time is a coordinate, a line that we move along, and secondly, a proper time-centric model that uses the imaginary time metric, where this dimension is a loop, and the progression of time that we experience emerges from the system as a whole. 2 mathematically equivalent models, but with profound metaphysical differences, and it is those differences which the Dirac equation and quantum mechanics more broadly highlight. The concept of negative energy is not compatible with the concept of a timeline, and so the discovery of the positron disproves the orthodox interpretation of relativity. If a timeline were physically real, antimatter would disappear into the past. The so-called time dimension is not time, and we have misunderstood this due to the way that it influences how time is experienced. Thank you.